Welcome to the optical communication course. Today we learn here the that scattering we have seen in the last lecture, and then we have seen some fact about the mass scattering there in the last lecture, and then we have stopped at that time. Okay, mass scattering is nothing but a that mass scattering occur because of that non-perfect cylindrical structure. Non-perfect cylindrical structure means if you see that the optical fiber, in that optical fiber we have that core and cladding boundaries are specified there. So this one is about, we can consider that a core of a fiber core here, and then this one is nothing but what we have the a cladding, and this is about your axis of a core. Okay, we can say that this one is about the axis of a core. Now your signals are propagating through this fiber, means we can say that signal means nothing but a light rays are propagating through the found fiber that are reflecting from the boundaries of the core and cladding. Okay, signals are reflected at the boundaries from the core and cladding, and that signal, that rays, makes the angle that will be greater than the critical angle. Then and then they are reflecting. Based on this size of a core, that aperture changes. We can say that what will be the acceptance angle of this particular fiber and all, and that based on that we can say that ENA changes, numerical aperture changes. Now here in a Maya scattering, that cylindrical structure is not perfect. Okay, non-perfect cylindrical structure. Means this is a cylindrical structure, so it is not perfect. Some imperfections occur. Okay, that some imperfection occur here likewise at the boundaries of a core and cladding. So, or we can say that some irregularities occur at the core and cladding interface there. Or there may be a, there may be a small difference in a core and cladding refracting index at this particular boundaries. So because of that, or because of that structure, suppose I am saying that this is about a fiber, and because of that imperfection here, now this diameter is different here. Okay, there is a small variation, so that's why there is a change in the diameter of a fiber. Because of the change in the diameter of a fiber, so it will not form a cylindrical structure. So that imperfection occurs, and that imperfection gives us a scattering there. At this particular boundaries, there may be a scattering of a signal takes place. And that why this imperfection occur there? Because of at the time of a manufacturing, small variation occurs, and that variation may lose the cylindrical structure there. So means it is about a solid when we are manufacturing the fiber. So it is in the form of a glass, and that glass is in the liquid form. And then we are cooling that particular, and we are making one perfect material, that fiber, using that glass. When it is cooling, so at that time some action takes place. That action is about a imperfect structures, or there may be a strains, there may be a bubbles at the particular boundaries or inside the particular fiber, and because of that, at that particular bubble or at this particular um, boundaries here, suppose when signal reaches here, that will be scattered. That will be scattered in any other direction. So we can say that a signal scattered in any other direction there, or sometimes we can say that that signal may propagate through the cladding there. So that is nothing but a part of the signal may radiate it, and that radiation takes place, and due to that radiation, your signal get okay reduced there. Means you at the here that level reduce. Signal level reduce, and that because of that imperfection. Okay, because of that non-perfect cylindrical structure, and this is about it. But that uh, non-imperfect cylindrical structure occurs at the time of manufacturing. Now, how to improve or how to reduce the Maya scattering loss? To reduce the Maya scattering, we need to remove the imperfection due to the glass manufacturing process, or at the time of manufacturing the fiber, we need to remove the imperfection there. And then again at the time of manufacturing, we need to carefully see the what will be the boundaries made by this particular fiber, or we can say that what will be coating used to the fiber there, or we can say that we can increase the fiber guidance by increasing the relative refractive difference index. Means that n1 and n2, we say the difference, if we increase, then guidance mechanism will be increased. So these are the ways to reduce the Maya scattering. But how this Maya scattering occur? The Maya scattering occur due to the non-perfect cylindrical structure, irregular surface at a core and cladding. There may be a difference of a refractive index N1 and N2 there. Small variation is there. Means small variation in the N1, or we can say that because of that non-perfect structure, the diameter of a fiber may change, or a presence of this particular strains or bubbles. This Maya scattering will be occurring. Next about a non-linear scattering. Okay, non-linear. Now, in a non-linear scattering, so what happen here? Because a signal propagating means we can say that light rays are propagating through the fiber, and then they have some particular power. Means we can say that a rays or a modes propagating through this fiber, that how they have some particular power. Means signal has a some optical power. Okay, we can say that it is nothing but some particular optical power. When light is propagating from one mode to the another mode, okay, so when that power will be increased here. Okay, signal, we can say that that particular optical power, that light rays, if it is increased, because of that increasing in the power, so the fiber is not able to support that power, or you can say that that rays have the higher maximum power, they are not supported by the fiber, and because of that rays are not supported by this fiber, or mode is not supported by this fiber, then that signal is radiated inside the fiber. So that radiation takes place because of that high power. It may be a backward radiation, or it may be a forward radiation. Likewise, means your signal radiates in the form of a back forward one, or in the form of a backward one. Means radiation takes place in the form of a backward or a forward, or in the radiation takes place in the different mode or a different frequency. So this depends upon that how much is the critical optical power supported by this fiber. Means every fiber, they have some particular threshold level. Okay, they have some particular threshold level, so that your optical fiber sustain that optical power, and that optical power can be propagating through the fiber. If that optical power is larger than the critical value, then your fiber will radiate that particular rays, and that rays will be for in the form of scattered, means it will scattered, and it will forward it in the forward direction, that scattering signal, or in the backward direction. And that happen when your rays are propagating through the fiber, they are above the threshold power level. Okay, your signal is above the threshold power level, then and then your signal get, what we can say that if your rays are propagating above that threshold power level, then a scattering takes place. And that scattering is called as a non-linear scattering. And that non-linear scattering means signal propagating forward and backward. So that's why there may be a variation in the mode, and due to that, there may be changes in the frequency. Means we can say that there may be a shift in a frequency. We can say that there may be a shift in frequency, and due to the shift in a frequency, your signal get attenuated because signal is not supporting that particular mode or that particular power level. Signal get attenuated. Means attenuation takes place because of that particular power level. So that's why we should know that a fiber operating at what particular wavelength, because everything is occur at particular wavelength. If that wavelength changes, if supposed to be we say that a fiber operate at some particular wavelength, suppose I am saying that it is will operate at 800 nanometer now, and above that 800 nanometer there may be a scattering occur. But that scattering means what? A non-linear scattering due to the threshold power. Okay, linear scattering and non-linear scattering. So there are the two types of a non-linear scattering. One is about stimulated beryllium scattering, and another is about Raman scattering. Now, in this stimulated beryllium scattering, there may be a what happen? There may be a optical frequency shift. Okay, there may be a what? A optical frequency shift, and that optical frequency shift that varies based on the scattering angle. Now that rays are propagating, we say it will be in forward rays or a backward rays there, in forward direction or backward direction. Means that scattering will be takes place in the forward direction or backward direction, because that optical power is above the threshold level, and then there may be a shift in frequency or there may be a attenuation. So now here is the optical frequency shift that varies with the scattering angle, because if you see that the frequency of sound waves varies with the acoustic wavelength, and that particular frequency shift that will be maximum in the backward direction. That frequency shift that will be maximum in the backward direction, and that will be zero in the forward direction. Means your signal will be forward, instead of forwarding it will be in backward direction, because that shift occurs, it is in a backward direction, whichever the shift frequency shift is occur in a backward direction, and zero in a forward direction. Okay, zero in forward direction. Means it is in a maximum, but here it is in a zero in a forward direction. Means signal is backward here, so that's why it is called as a stimulated beryllium scattering, or we can say that a back scattering, and that occur above the threshold power level. So how, at what particular threshold power level, we need to calculate that what will be the operating wavelength and what will be the fiber diameter, because your wavelength and everything is changed based on this particular core of the fiber there. So that is about a simulated William scattering. Pb is equal to what? 4.4 into 10 to the power minus 3 into d square into your lambda square, and we have that alpha dB, that is the attenuation per kilometer, and depending upon that source bandwidth for a, if it is in a laser fiber, then it will be in a gigahertz there. This is about your source bandwidth. Now this here, this one is nothing but what? A power threshold power. Okay, this one is nothing but what? We can say that a threshold power for this stimulated beam scattering. And this d is nothing but what? A diameter. D is nothing but the diameter here, and this lambda, that is about your operating wavelength. This one is about a operating wavelength, and this one is nothing but what? A attenuation per dB kilometer. So we can say that we have the dB per kilometer there. That is about your attenuation. Okay, so that is about a scattering that will be occur when we have the power above this threshold level. When your signal propagating, we say that optical power propagating through the fiber, that will be above this threshold power, then and then a scattering occur, and that is called as a stimulated William scattering. Then next one is about a Raman scattering. In the case of a Raman scattering, so earlier we say that there may be a shift in a frequency, and because of that a shift in a frequency, there may be a variation in the frequency of a sound, because generally we say that because of that shift in frequency, your angle varies, that scattering angle varies, and because of that varies in a scattering angle, the frequency of a sound varies with a acoustic wavelength that we have said in a stimulated William scattering. Now, in the case of a Raman scattering, so what happened? Here we have the high optical frequency we consider, uh, or we can say that the same thing here. We have the fiber core and all. We require that sufficient optical power. Okay, here we can consider that is about a optical power that will be the above threshold level. Okay, that will be above threshold level. But in the case of Raman scattering, if your signal or your rays that up that more than this optical power, if your light rays are propagating, or you can say that signal propagating through this fiber is more than this optical power, more than this threshold optical power, then that scattering takes place. Scattering takes place either in the forward direction or in the backward direction, in the both the direction. So in this particular Raman scattering, so that threshold power, that will be greater than the stimulated beryllium scattering, and this scattering occur because of that whichever the non-linear structures in the particular fiber at a high optical power, and that loss introduced because of that optical high optical power, and then scattering will be takes place. That will be a non-linear scattering, and that will be above the threshold level. Now, if you consider that a single mode fiber, then a stimulated beryllium scattering occur in that fiber because earlier we say that optical power, threshold optical power, is depending upon that diameter of the fiber. So that's why if the diameter is increases, means that diameter, core diameter of fiber is increases, then we can minimize or we can reduce this stimulated beryllium scattering or a Raman scattering. But all this scattering occurs in the single mode fiber. If we are using a multi-mode fiber, then that multi-mode fiber, the diameter is a large. Due to a large diameter, this type of scattering will not be occur there. And generally, this scattering is occur if we have the wavelength is the smallest one. And to reduce this scattering, we have to use the longest wavelength. So this scattering is occur if we have a single mode fiber. In a single mode fiber, the diameter of core is small. That's why that scattering is occur. So for the multimode fiber, okay, if we have a multi-foot fiber, it has a large diameter. Because of that large diameter, so no scattering takes place. Okay, because of that large diameter, no scattering takes place. And this, and again another thing is that if we use that a longest wavelength, okay, if we use for long wavelength signal, for a long wavelength signal, that scattering will be reduced. Miss Raman scattering reduces if we have the long wavelength signal. So for if we that wavelength is a small, means long wavelength means what? For example, I am saying that our signal is about the 800 nanometer of a wavelength, and if you see that attenuation curve and this particular graph, so above that 1200 something, that no scattering takes place. 1200 nanometer now. But at the 800 nanometer, there may be a scattering. But the scattering will be of a single mode fiber due to the single mode fiber. Now the equation for the Raman scattering, that is about a PR is equal to 5.9 into 10 to the power minus 2. We have the diameter there, then we have the wavelength, and then alpha dp. Okay, so that is about our power. So here we can say that this one is about a diameter, this one is about your wavelength, and this one is about your attenuation. And then this is about a threshold power. Okay, this is called as what? We can say that is about a threshold power. So above this threshold power, this one is the threshold. Above that particular power is scattering occur. That is called as a Raman scattering. So next we will see that if fiber band loss, how this loss occurs, what are the various attenuations occur, how your signal distorted. We are learning here the signal distortion. So any signal distortion because of that attenuation, because of that intrinsic or you can say that it's about the extrinsic attenuation there because of that material. Okay, Signal attenuation takes place because of that material is used. And signals are attenuated because of that scattering. Again, attenuation occurs when we another mechanism of attenuation. If we bend the fiber, then there will be a loss. Then that loss is called as a fiber bending loss. Then we should know that what will be the critical curvature of the fiber band. Now, supposed to be this is about your fiber here, and this one is about a curve now. We say, and for this given particular curve, what will be the radius of this particular curvature? If that curvature radius is reduced or it will be increased, so what will happen? So we need to know about what will be the critical radius of this particular optical fiber at a bend so that loss can be minimized. Okay, that we have to see here. So generally what happen? Your signal is propagating through the a core. Okay, means mainly we have the axis there. Okay, for a given particular fiber, they have some particular axis. And what happen here? At the particular bend, we generally say that signal are propagating through the fiber. But because of that bend, here the velocity of that particular rays are increases because of that bend. And then at the end, we are we are just expecting that there may be a plane wavefront. But because of that particular bend, signal may propagating through the cladding. This is about a cladding layer. So if you see here for a given particular fiber, so now your radiation pattern of this fiber is likewise. Here is the center is maximum, and this is nothing but you can say that is about a radiation occur. And this one is about your cladding now. Your signal get radiated here at this particular boundaries of this particular fiber. And generally we are expecting that a fiber having this there will be radiation. But radiation will be increased, okay, because of that particular fiber. So ideal case this may be a radiation, but radiation will be more here, okay, because of that fiber curve. If we use a large bend, okay, if we use a large bend, then we can minimize that loss. Okay, so large bend means we have that radius will be large there. So there are the ways we can say that small bend or a large bend, okay, and they are according to that they have the types of loss. We can say that a micro bending and a macro bending loss. Micro bending means what? This type of loss we can say, or we can say that there may be a loss that is about to occur at the corner of a fiber, because when we use a fiber and we turn the fiber, so that's why that macro bending occurs. Micro means because of that in a given particular fiber there may be imperfections because of that bend. That is called as a micro bending and macro bending. So imperfections occur when we use a fiber for the long distance, and always it will not be a straight one. So somewhere we need to take a curve and all, or somewhere we have the corner there. So in that case, we need to bend our fiber. So at the bend, if you see that radius here it is small, but at the particular bend, that radius will be increased here. Means a macroscopic bend, we say that because of that particular bend, there may be a variation in this particular radius occur, and that radius is because of that bend, radius is variation is occur because of that bend, and that variation is that radius will be large as compared to that at actual core of a particular fiber because we are bending the fiber. And in the case of a micro bend here, because there may be a small variation in the that bend occur, small imperfections at the boundaries, and because of that small imperfection, that axis may vary. Okay, here if you see that a fiber core, the radius may be vary. So if you see that generally it is about a core axis, and because of that particular imperfections at the boundaries, so that axis may vary here. Fiber core axis may vary. So, and because of that loss occur, that is called as a micro bend loss. And here we can say that is about the macro bending loss. So there may be a large bending loss occur if we are using a multimode fiber, and that fiber will be used at a critical curvature. So what will be the critical radius of a curvature? So critical radius of curvature here. So that's why that loss will be, there may be a large bending losses. So that is nothing but what RC is equal to 3 n1 square. We have the lambda, that is about the operating wavelength, 4 pi, and there may be n1 square minus n2 square. Numerical aperture again, yeah. Because if you see that this equation here is saying is about the difference of that n1 and n2. To reduce that macro bending loss because of that curvature, we can use or we can design a fiber with a large relative refractive index difference. It is about a 3. Okay, so this one is about a 3 here. If we want to reduce the macro bending losses, we need to design a fiber with large relative refractive difference. Large relative refractive index difference, so that we can minimize this macro bending loss. Or we can say that we can operate at shortest wavelength. We can operate at a shortest wavelength. So now one graph I have shown you, so in which it has mentioned that there may be a losses or attenuation occur because of that imperfections and all. So that losses is called as a relayed scattering and all, or you can say that is about the waveguide. So this graph is saying that a relay scattering reduces if that there may be a large wavelength, longest wavelength. But absorption is about the, yeah. So absorption or a waveguide imperfection, and because of that there may be attenuation loss. So similarly, if you see that in the case of a bending micro that fiber have the bend, if we are using a shortest wavelength, so we can reduce the whatever the bending losses, and that is called as a macro bend loss. Okay, if we reduce that what will be the operating wavelength, so we can reduce that uh, bending losses. But this is about for that curvature is for the multimode fiber. It is for the curvature for the multimode fiber. Now, if you consider the single mode fiber, then RC will be what? A 20 lambda. RC will be 20 lambda divided by N1 square minus N2 square raised to 3 by 2 raised to 3 by 2 into 2.748 minus 0.996 to lambda by lambda c raised to minus 3. That is about your, if we are using the single mode fiber, so we can use the that critical radius of a curvature, and if that radius is increases, this critical means what you about a smaller radius. Okay, the bend will be have a small radius. If we have the large radius, yes, so like, sorry, this is about a smaller radius now. Okay, sorry, this one is of a small radius. If we use a large radius, then bend may be reduced. If we use a large radius, the bend may be reduced. Okay, so means that bending loss is depending upon that radius of the curvature there. So we can minimize. Okay, we could not remove the bending loss. We can minimize the bending loss. So we should know that at what particular critical values, so that loss can be reduced there. Next topic we will learn here, that is about a dispersion. In the case of a dispersion, what happen? Whichever the signal transmitted from this optical fiber core for the longest distance now. Okay, you just consider that is same. Okay, that core size is same now. We have about a particular length of the fiber. If that fiber length is increased, so there may be attenuation. Similarly, if that fiber length is increased, there may be a dispersion. Dispersion means what? Because that optical signal level change here. Here we say that a signal is transmitted through the optical fiber, that is a current pulse, and we are receiving that current pulse will be broadened there. Because transmitted pulse is a small width and receiving pulse is having the broader width. Means that pulse broadening takes place inside the fiber. And why this broadening takes place? Okay, we'll see in detail now. So generally we say that a source, we are providing the current, and then current is converted into the form of a light rays, and then it will be propagating here. And at the end we have a receiver, we convert again into current, and then we'll get that at actual pulse. Here the pulse broadening takes place. So means transmitted signal from this end, and you can see that a receiving signal at this particular end. If you see the signal level, and if you see the width, okay, if you see the width and a level of the transmitted signal and receiving signal, so you can see that there may be a, we can observe that that width is increased. Again, that level is reduced. If we further increase the length of the fiber, okay, if that length of the fiber, even if we further increase, so then your pulse may be likewise. If we increase the fiber, so it will be broadened and that level is reduced here. So this mechanism of broadening of a pulse is called as a dispersion, And that pulse broadening occur when your pulse is travel along the fiber there. Okay, along the fiber. Now what happen if your pulse is broadening there? Now we take one example here and we'll discuss about that what happened to the pulse broadening. Generally we consider that a train of pulse is propagating through the fiber. This I am taking one example, simple example, and that train of pulse is nothing but a current pulse, and that current pulse is in the form of one and zeros. This is nothing but one. This one is about a gap here, zero, one, in the one. Okay, that is about we can say a amplitude here, and in this case here we can consider the about a time here. Because when pulse travels, so it takes a time. So that's why for a given particular time, what will happen to the given particular pulse. Now, the same pulse we are receiving at a distance, some particular distance there. So what will happen to the particular our signal now? Now that when we consider that a input signal, this is nothing but the input signal to your fiber. Okay, this one is about the input signal to the fiber. And because of that pulse broadening occur at a distance, at a particular distance, then what happen? That pulse broadening takes place. Means what happened to our signal is likewise. Okay, so now here that is the overlapping takes place with a 1 and 0. Now this one is about our signal 1, this one is 0, 1 and 1. Now if you see that here, so there may be a small portion we can say that is overlapping of pulse takes place there, and because of that overlapping of pulses, so this signal or this particular one is up to that particular distance now. This is up to that distance. Now at what particular time that this particular one has started or one has ended. Now another case we consider here, if the distance is large now, if the distance is large as compared to, this is about a length of the fiber, that is we consider that is about L1. If that length is large, suppose we consider that another length, here supposed to be 1 kilometer. Now for the 10 kilometer what will happen? So for the 10 kilometer what will happen? Your signal may be overlapped here. Okay. So now if your signal overlaps, so this is about a intersymbol interference occurs here. Likewise, this is the called as you can say intersymbol interference. And because this one is about your signal, we say it is about a 1. But this signal, if you see that, if you compare here, so at this there is some particular level is increased. So 0, okay, we are expecting that 0 level, but it is about a non-zero level right now. Because 1 0 there we are saying 1 and 0. So here because of the distance is long, length is more, so that's there is about a 0 is not identified. Now next, if you compare that this particular portion here, if you compare this particular portion, so there is throughout this one we are saying